also clustering. So clustering is another way, another set of methods for unsupervised learning. And the same goal holds here. So what we want to find is some interesting features behind our data. But now the type of features, well, some interesting characteristics, not to overload the feature word. But now we want to find like other type of characteristics behind our data, and the type of characteristic that we want to find is if there is some type of grouping occurring in your data points that maybe reveals something interesting about the data. So this is again unsupervised learning, because even though it seems like classification, it's really not classification, because we don't know the labels for any of the groups. There are also like some approaches that are semi-supervised learning. For example, in anomaly detection, sometimes you have a combination between clustering and classification, because yeah, in some cases you may have a few observations that tell you, okay, this can be regarded as anomalies, but maybe like the big majority of observations are not labeled. So in those cases, you will be like somewhere in between, in a semi-supervised setting in that case. But for today, we will be looking at the unsupervised approach. So we don't have any labels at all in our data, and we just need to find what are the groups that can be formed. So then this type of methods, of course, are useful for many applications. So for example, we can organize some data. We can also we can understand. Actually, I can go to the next slide. So sometimes it's also used for example, in Netflix and in Spotify and other applications. Sometimes you can learn a lot about some customers based on what other customers that share similar behaviors are doing. And this often is referred as collaborative filtering. So this is like how can you learn about some of the subjects using information from similar subjects. Of course, there are like some clustering algorithms for community detection, and yeah, this for this like some of these networks, social networks data sets are very interesting to analyze. Of course, you can also cluster different news articles or websites by what type of information is contained either in the article or in the website. And well, I wanted to share also like this application that it's somehow related to social topics and to public policy. So this was like 5 years ago. I collaborated with there is a Mexican institution that gives some economic support to vulnerable groups, and they wanted to learn if there was a way to group households so that you can identify which type of households have similar characteristics, so that you can target some vulnerable groups and give different types of benefits. This type of clustering that we came up with a method that is a bit more complicated than the k-means that we will review today. But of course, you can see like this other type of clustering, because the type of clustering here is a Bayesian method. So this is also like a model-based approach for clustering. But I guess it's just important for you to know that clustering is very, very relevant for many applications in social policy. So in this other plot here, this is one of the plots that come in the welcome page of sklearn for clustering. And here you can see that depending on what is the structure on your data, there are many different approaches that you can use, and you can so you can capture different types of grouping by using different algorithms. So in general, I would say that there is not a single algorithm that outperforms all the others, because it's also a bit hard to say what metric do you use for to say that it's outperforming. But you can see that some of the algorithms, for example, are good at capturing like these two donuts. Some of them are better at capturing like these kind of normal shapes. Yeah, for example, this one was good at this one, but maybe not that great at this one. Whereas on this one is better at capturing this type of structure. Yeah, so the point here is that the method that we will review today is more like to create some intuition behind clustering, but I would encourage you to try different approaches for the data set that you want to analyze. And the principle is very similar, of course, like it's just finding groups behind a set of features, and that may reveal something interesting in your data. So let's jump into k-means clustering. So this is one of the most basic algorithms for clustering. And the idea is that the method works by iteratively assigning different groups to your data and using some centroids to represent each of the different groups. So we begin, one important parameter here is that we need to choose in advance what is the number of clusters that we want to find. And then this number of clusters k will be used as a hyperparameter of your algorithm. So then we will see some methods for finding the value of k that somehow like capture the the best of, well, somehow reflects the structure of your data in a better way. But yeah, so let's jump into the details of the k-means clustering. So the idea here is that you receive, as in principal component analysis, you receive a set of data points, but yeah, and all this data is just the features x, and you can see that of course there is no label y. And the goal here is to assign each one of these observations in your data set to a given cluster. So you start with the number of clusters k, and the idea is that you want to assign every element I in your data to one of the k clusters. And to do that allocation, then there are two parameters in the model that you will be training in this case. So one parameter is, well, one set of parameters is the cluster centers. So this is like the centroid of the cluster that you are estimating. Well, maybe not yet. But yeah, so one parameter in your model is the center of the cluster, and the other is the allocation of each data point. So because you have n data points in your data, then you will have n allocations, n assignments of each point to a given cluster. So then the value of these assignments, of course, is just a categorical value going from 1 to k, because you have k clusters. And yeah, and once you know the parameters of your model, then the decision rule is just to assign a new data point to the nearest cluster center. Yeah, so basically just like any new data point is assigned to the cluster whose centroid is closer to that data point. And one way to understand this algorithm is that the function that we are minimizing for solving, for finding these parameters in the model is we want to minimize this distance. So the idea is that we want to find the centroids that, we want to simultaneously learn the assignments of the cluster and the centroids. The assignments of the data points and the centroids of each cluster, so that we are minimizing the distance of each point to the corresponding centroid. Does this make sense so far? We will see that in a minute, more practically. So the algorithm, how you can minimize this this loss function, we can do it in an iterative approach using the EM algorithm. So basically, you start with the data x1 to xn, and then you can initialize by assigning threshold, groups to each of the data points, and the original assignment can be just a random assignment. So you can just select a value between 1 and k randomly for each of the data points, and then you start the EM algorithm. So at each iteration of the algorithm, you first assign the cluster. So for observation I, you look at the centroids for the k clusters and assign the cluster with the nearest centroid to your data point, and then repeat that same assignment for all the data points in your data. And then once all the data points have been updated, then you recompute the centroid of your clusters. And this is just by taking the mean between all points that are assigned to the cluster J, and J goes between 1 and k. So this is pretty much the EM algorithm, and just in the E step we update the cluster allocation, and in the M step we recompute the centroid of the cluster. So this one looks like this in practice. So here we're showing just the evolution of the algorithm at different steps. Just at different steps. So we start with this type of data. Let's imagine that the data that you receive is only contains two features, like x and y, and you want to find clusters for this data. And let's assume that you start with just with the assumption that k is equal to 3. So you want to find 3 clusters from this data. So in the first step, as the algorithm said before, so we initialize the clusters for all our data points, and we can initialize it just randomly. So before looking at anything, so you just assign any of the 3 clusters to each data point. And then once you have all these random assignments, you can compute the centroids for each cluster by averaging the values of x for each of the data points in the corresponding cluster. So because in the first step everything was random, then of course the centroids in the first recomputation of the centroids in the first stage will be very close to the center of the data, and they will be very similar, right? But then once you have the first values of the centroids, you can update the allocation of each data point. So once you are here, you assign each of the data points to the closest centroid. So in this case, because just randomly the yellow centroid was on top of the other two centroids, then we see that all these points go into the yellow cluster, and similarly to the others, right? Like the red one is here on the bottom left, and the green one is on the bottom right. And then you just repeat the same procedure. So in a new iteration, you recompute the centers of the cluster by considering all the points that are in that cluster, and then the centroids are updated like here, here, and here, and then you just repeat again. And after a number of iterations, you will see that the algorithm converges. So the algorithm converges when you don't see any new change in the allocation of points. And this is guaranteed to converge. But something important is that, maybe just like for some participation, do you think that this algorithm converges always to the same solution? Or, and that solution is a global optimum or a local optimum, or so let's say first, do you think that the algorithm converges to the same solution every time you run it? No? Why not?
I mean, the first step is random, right? And that depends on state of the computer, so I guess not, because that changes over time.
Exactly.
Yeah.
It's just a random initialization, and therefore, the algorithm is not guaranteed to always find the global optimum, but only a local optimum.
Does this differ for different problems? Because we had a similar problem, but it was two Gaussian distributions we had, and I toyed around a little, like how can I manage to break the ML algorithm? Because here you started out, but you initialized it by guessing what the parameters of the Gaussians are, and the only way for me to break it, to have it arrive at a wrong solution, was by having both the parameters of both distributions be similar. But even if they were just slightly different, it would always converge at the same solution. It would just take more iterations.
I see. I mean, it's very common that the majority of the like if you run it 1,000 times, maybe 990 will converge to the same solution. But that doesn't mean that it's guaranteed that it will always land in the same solution, right? So, of course, as we will see now, if you repeat the same algorithm just with different random initializations, you will see that the clusters assigned often coincide like in different runs. So, for example, here, the algorithm was run 6 times, and 4 out of the 6 times the same clusters were found. Of course, like there can be like some label swapping, but the groups that were found are the same, like in these 4 solutions. So this k-means, of course, is not always finding a global optimum, but rather a local optimum. And it's important that if you use this algorithm, just like keep in mind that this is the case and try to run it many times and select the solution that minimizes the cost, the loss function that we said before. So this is basically computing the distance from each observation to the centroid, to the associated centroid. So this is the distance. So just compute this loss and choose the solution that minimizes the loss. So in this case, any of these 4 will be chosen. And then the next question also that is very common to ask for k-means clustering is just like how many clusters should you decide for the hyperparameter k? And this, like in comparison to cross validation, is not you will not see like a U shape in which you reach a minimum for a given test test error. But in reality, what you see is that as you keep increasing the number of clusters, of course, the distance, so this loss function will just keep decreasing, right? Because, I mean, think about it, in the extreme case, you have one cluster per data point, and then of course your error is 0. So as you keep increasing the value of k, your cost will keep reducing. But one popular heuristic is to use this elbow method. So this is basically choosing the value of k, after which the loss is saturated, right? Like after, maybe here you can see that by using 3 instead of 2 groups, you are still reducing quite a lot the cost function. But then the difference between 3 and 4 is not really that significant. So there is no need to increase the complexity of your model by introducing one more cluster. And similarly for values after 4. So the idea is that you just use the minimum number of clusters that capture most of the underlying nature in your data. Yeah. So any questions? Yeah.
When you say that loss is saturated, do you mean it converged?
So the algorithm is converging for every value here. So this is not representing the iterations in the algorithm. This is representing, so each of these ones is already a converged solution.
Okay.
But this is, let's say, like if you start with k equal to 2, then the loss, perhaps if you run multiple times the same algorithm, you would have a few values here, right? So these are like these numbers over here. So let's say like this 235 is representing this point. Of course, you may have some noise here after convergence, but let's say like for the minimum of those points, you will see that number is reduced if you increase the value of k. And just like after some point, it's like you cannot reduce it by a lot. Yeah, and then just like beyond tabular data, these clustering algorithms can also be used. Like in particular, this k-means cluster is a popular way to for image segmentation. So you can do the same, just like the same clustering on the pixels of an image, and yeah, and somehow it's also like capturing the underlying structure of your image. So here it's just showing if you use like 2 colors or 3 colors or 10 colors, how the image segmentation results by using this k-means cluster. So in this case, it's just your variables would be just the red, green, blue channels, and the image is so the color that it's being shown here is just the value at the centroid of the cluster. So in this case, we have three groups. One group is like this blue color, then the yellow and the dark color, and this is just like the average across all points that belong to the same cluster. So in this case, when k is equal to 3, like the skin and this yellow color of the game is clustered in the same group. And similarly here, you can see that the more clusters you have, the image resembles more to the original image. But I think it's nice that some of the information underlying in the image is captured by only a few clusters. Yeah, and I think that's it for this clustering. Of course, as I said before, like I would encourage you to try out other algorithms for your data set. And yeah, and now that you have chosen your data set, maybe you can, I wanted to cover first unsupervised before jumping back into supervised with hierarchical models, so that now you have a full set of algorithms that you can play with your data. So you can start visualizing with PCA, you can start doing some clustering to understand your data, or start predicting with basic methods. And then in the second, well, after this class, we will review more advanced methods for supervised models that capture more like hierarchical structures and deep learning and so on. But yeah, so if there is no more questions, so yeah, let's close it for today.